There was a good study with the Buddha group at Stanford showing very broad distribution of particles from incipient wetness, oxidation reduction, and it concluded that the most catalytic reactions are not structure sensitive. It doesn't matter what the particle size in this distribution is, except maybe ammonia synthesis. That was very visibly structure sensitive. So what we find with this product distribution, and my postdoc, who is now a great industrial scientist, Pushkarev, found that as you change the particle size, you can change the test reactions which are used for most oil companies, benzene hydrogenation or toluene hydrogenation, changes by a factor of 4. And this is, means $100 million a day for making high-octane gasoline. But in fact, the size dependence of the turnover rates were crucial. Now, when you change the size, of course, the top shows the size dependence of the same shape. You can also change the shape, and both of them are catalytically very significant. Now, so now we go to nanoparticles because it's obvious that it changes the turnover rates and the selectivities, sometimes one more than the other. And so you can do it in 2 dimensions with the Langmuir-Blodgett formation of nanoparticles in various concentration, or by sonication, or other ways you put it into a mesoporous materials and you go to 3-dimensional. Now, what is very interesting and very well known now is that by hard templating, as opposed to soft templating, you can take a mesoporous silica like SBA15 or MCF17 and coat it with a transition metal salt, and you oxidize this, and then you leach out the silica from that, and you left behind with a mesoporous material of the transition metal oxides. And then you can disperse the metal inside that. So you can make mesoporous supports of various oxides and put metal nanoparticles inside with the same dispersion that you desire. Now, the other way of making very interesting structures is the core shell structures, where you have a metal core and then you put a silica shell which is mesoporous in there. And these structures are very important if you want to do high temperature catalysis. The metals of the size that you desire, sometimes 5 nanometer or 3 nanometer size, have a much lower melting point than the bulk materials. So if you go to high temperatures, platinum or gold or any transition metal melts at a lower temperature than the single crystal, okay? Hundreds of degrees lower. And so when you want to do combustion chemistry, this is a problem. However, if you have a silica, mesoporous silica coating or alumina coating, then what you find is that you can go to 900 centigrade before these particles melt. It's still not the bulk melting point, but in fact you can do combustion catalysis around 900 centigrade or so. Now, let's just talk no acid base, just look at metal nanoparticles, covalent bond catalysis. And this is the final conclusion. The size and shape controls both catalytic reaction rates and selectivities. And the way we studied that is study some simple reactions which have multiple products. For example, look at crotonaldehyde. Crotonaldehyde here has 2 double bonds, CO and CC double bond. You hydrogenate, you either get crotyl alcohol, partial hydrogenation, or butyraldehyde. And then you go on to full hydrogenation of butanol or butane. So all these other reactions, pyrrole hydrogenation, furan hydrogenation, give you several products, and you see how the selectivity depends on the size and shape. And so what you find is that as you change the size, this is benzene cyclohexene hydrogenation to dehydrogenation selectivity. You make benzene at high sizes, and you make hydrogenation at high sizes, and you make benzene at smaller. You make benzene here, which is small particles like to dehydrogenate. The big particles like to hydrogenate. You take furan, you see partial hydrogenation, and as you change the size and the crystallography, you change the product distribution from one product majority to another product majority. This was decarbonylation of furfural, which is a product of partial biomass conversion, and you find that in small furfural, this one is making mostly furan. It's a decarbonylation mechanism, and when you go to big particles, you get hydrogenation to furfuryl alcohol. And so let me give you one shape-dependent catalysis, and this is methylcyclopentane. Methylcyclopentane can isomerize in all these isomers. It turns out that when you change the shape, the isomer you get is shape-dependent. Okay, a very interesting case. The turnover rate doesn't change much, but the product selectivity changes dramatically. Now, the question is why? Why is selectivity and turnover rates size and shape sensitive? This is, I think, the fatal fault of catalysis, is that most of the studies were not done under reaction conditions when you see the dynamics, but you're looking at either the reactant or the product, and you conclude what is in between. I mean, if you look at the fetus and the dead body, you can see how much less that you can learn by looking at life itself. Now, the atomic level characterization is under reaction condition. And I spent about 20 years to develop these techniques that can look at the reaction look at the catalytic reaction under catalytic reaction conditions. And the techniques, it seems, gained tremendous footing in synchrotron radiation. And while the some frequency generation, the top was a Berkeley development by Ron Shen and myself to do vibrational spectroscopy under high pressure or solid liquid interface conditions on the interface. The other synchrotron techniques gave us oxidation states, coordination numbers, and microspectroscopy at the solid liquid interface, all of them under dynamic reaction conditions. The high pressure scanning tunneling microscopy was one of these techniques, but it has problems. We cannot image nanoparticles with STM, but we can image single crystals. And so that's a major drawback. And the nanodiodes I will get to. So the some frequency generation, which is two laser beams, one of them infrared, the other one visible. You keep the visible frequency constant, and you get you tune the infrared frequency. And this has both Raman and dipole selection rules. And the bottom line is, if you have a central symmetric environment, either a central symmetric solid or a gas or a liquid, this signal, the sum frequency signal, is zero. However, at the surface, it's non-zero because non-central symmetricity of the surface makes this sum frequency vibrational spectra alive. And so as a result, you can see reaction intermediates. If you look at ethylene hydrogenation, you can see 3 species on the surface. One is the one that turns over. These 2 are spectators. Okay, but you need isotope studies, etc., to distinguish. You see all 3 with vibration spectroscopy. If you do cycloids in hydrogenation, you see the cyclohexadienes, 1,3 and 1,4 cyclohexadienes, and also these allyl reactions. The bottom line is we almost never see the product or the reactant, but we see something in between. But this is not exclusive. We have to do more to make this more conclusive.